we've made the next section optional. It's not mathematically too complex, but we don't think it is necessary to understand the whole thread of today's module. However, for those interested in a little bit more detail or another interpretation why overfitting happens in logistic regression and why it's so bad, we've created a few other examples for you to go through. So this part really explores that and really explains why those parameters become really massive in logistic regression. So let's dive into it. To understand a little bit better of why overfitting happens in logistic regression and why the parameters get really big, we need to introduce the notion of linear separability. Now, linearly separable data is more or less what you'd expect. There exists a line here where everything on the left of the line, in this case, has score of x less than 0, and everything on the right of the line here has score of x greater than 0. So it separates the positive examples from the negative examples. More generally, we say that the data is linearly separable. Somebody stops you in the street and says, what does it mean for data to be linearly separable? We say it's linearly separable if the following is true. It's linearly separable if for all positive examples, score of x, which is w hat transpose h of x, is greater than 0. So it's greater, strictly greater than 0 for all positive examples. And then for all negative examples, the score of x, which is w hat transpose h of x, is less than 0. And so what that means is that we're getting the training error to be exactly 0. And this is a really important point. Again, if you see training error getting exactly 0, you should start getting worried. And what you see is that the data is linearly separable, that's exactly happening. So you might think, oh, it's a great thing, my data is linearly separable. You should be careful because you might be getting into an overfitting situation, especially if you have a very complex model and you have perfect training error. Now I've drawn this in two-dimensional space, but if you have d-dimensional features, let's say 1,000-dimensional features, linear separability corresponds to a plane in a 1,000-dimensional space that separates positive examples from negative examples. That's my space voice, for those who didn't get it. So that's a way to think about it in high-dimensional spaces. And the other little side note, which I'm not going into detail, but it turns out that if you keep adding features like polynomials of degree 20, 50, 100, and so on, eventually, except for some corner cases, you're actually going to make your data linearly separable. So you might observe that with enough features, your training error will go to 0, which means you'll fall into exactly this linearly separable case, which is a very problematic one. To understand why that space is problematic, or linearly separable data becomes a problem for overfitting, let's look at this example over here. In this case, the plane 1.0 number of awesomes minus 1.5 number of awfuls separates the positive examples from negative examples. Now, what does that mean? That means that the plane 1.0 number of awesome minus 1.5 number of awfuls equal to 0 is the boundary between the positive examples and negative examples. Now what happens if I multiply both sides of that equation by 10? I get 10 number of awesomes minus 15 number of awfuls on the left side by multiply by 10. And if I multiply 0 by 10, I also get 0. So it turns out that that bigger coefficient also separates the data in exactly the same way. And guess what? If I multiply both sides by 1 billion, I still separate the data in the same way. So 1 billion times number of awesomes minus 1.5 billion times number of awfuls still separates the data. And so whether the coefficients are small or big, we still have a separating hyperplane. So why am I going to get pushed to these bigger coefficients? Well, to understand that, we have to go back to our probability of our data. So let's pick a particular data point here, one that's near the boundary, which has 2 awesomes and 1 awful. I really love that review. Two awesomes, one off was a review that I keep coming back to. Now let's see what happens to our estimating probability for this case. Let's see what happens when you're using the first set of coefficients learned. W1 is 1.0, W2 is minus 1.5. So in this case, my estimate of probability is 1 over 1 plus e to the minus, so 2 times 1.0, which is 2, minus 1.5 times 1, which is minus 1.5. So this is equal to 1 over 1 plus e to the minus 0.5, which turns out to be equal to 0.62. Now that makes sense to me. It's a point close to the boundary. There's 62% chance that it's a positive review, but then there's still 38% chance it's a negative review. So I feel really good about that prediction. However, since we're doing maximum likelihood estimation, we are pushing probabilities towards extremes. We're trying to learn parameters that makes those probabilities bigger. So let's see what happens when we use the second set of parameters, 10 and minus 15. So in this case, we multiplied everything by 10. So the probability is going to be 1 over 1 plus e to the minus 5 instead of e to the minus 0.5, which is equal to 0.99. Wow. Now, even though the point is close to boundary, we are 99% confident there's a positive review. That doesn't seem quite right. Well, let's see what happens when we look at 1 billion and minus 1.5 billion. Well, that ratio becomes 1 over 1 plus e to the minus 0.5 billion. And I don't know, my calculator couldn't compute that exactly. Probably yours can't, but I can tell you is basically 1. So when the parameters become, the coefficients become really, really big, I'm sure that they put that point right next to the boundary has probability 1 of being a positive review, and I don't trust that. However, maximum likelihood estimation prefers models that are more certain, and so it's going to push the coefficients to be infinite for linearly separable data because it just can. So it's going to be pushing to be larger and larger and larger and larger until basically they go to infinity. So that's a really bad overfitting problem that happens in logistic regression. So just as a summary of this optional section, we'll see that logistic regression overfitting here can be what I call twice as bad. We have the same kind of bad situation that we had looking at decision boundaries and typically in regression, where you have this really complicated functions that you learn, and you become, with really complex decision boundaries that kind of overfit to the data and don't generalize well. But you also have the second effect, where if the data is linearly separable, if you have lots of features, the data becomes linearly separable, or you're close to it, then the coefficients can get really big and eventually even go to infinity. And so you get this massive coefficients and massive confidence about your answers. And so you see these two kinds of effects of overfitting with logistic regression.